That's okay. So, today we are going to be talking about topic 12, optimization. I am recording this, just so you guys know. This is a new topic for the class. This is the first time we're running this topic. So, let's talk a little bit about what optimization is and what it means. So, in general, the idea of optimization is to write an algorithm that's searching for a minimum or a maximum of a function. And this often, at first look, appears to be a very simple problem because there's a max and a min function in MATLAB, so a lot of first reactions are, why would you need to write an algorithm to do that? But the idea is that A, you have data, not some analytic function that you can find the maximum of, and B, that there are multiple mins and max of the function. So, for example, you are interested in knowing what all of the optimum are. So you can see here, there's a local max here, there's a local max here, and then there's a min here. So a lot of times with optimum algorithms or optimization in general, you're looking to locate all of the optimum. And just for reference, this is very similar to, these algorithms are very similar to root finding algorithms. They use a lot of the same general like flow of steps and stuff. And so remember, root finders find where functions are 0. So the definition of an optimum is a point where the curve flattens out, or the derivative of the function is 0. So it's basically changing from increasing to decreasing or decreasing to increasing. So by looking at second derivatives and curvature, if you have the second derivative greater than 0, that means you have a minimum. And if your curvature is in the opposite direction, that means you have a maximum. And this is all familiar from just calculus, but these methods of optimization have been developed for finding optimums of functions where you aren't able to find the derivative of the data. So this could be from a variety of reasons, but it's mostly because you have data, you don't have analytic functions, but particularly with data that has very unpredictable behavior. So optimization problems in engineering are often much more complicated than just finding a min or a max, just a single min or a max or a single optimum. So some examples. There's a ton, and it becomes more and more complex when you add more and more conditions, basically. But design optimization is a form of this optimization, and it's all based off of this same basic principle of finding some sort of optimum, regardless of what that is. But it could also extend to like minimizing cost, and oftentimes when you're looking at cost, there's tons of conditions and constraints on that optimization. It's not just what's the minimum cost. There's a lot of different conditions and equations and variables that are all impacting it. Another common one is maximizing efficiency and minimizing error. Etc. So there's a lot of them. And so what we're going to talk about today is a very simple subset of this full optimization area. And optimization problems are categorized into different types. And there's a couple different types that we're going to just familiarize ourselves with, and then I'll show you the type that we are going to be focusing on with our algorithm for this topic. So the first thing to consider is the dimensionality of the optimization. So the one that I just drew up there is kind of like a 1D optimization where you have one thing varying, and so you're kind of looking at it from, you can think about it as a line plot. But you can also have 2D optimization and think about it as having like a field, some elevation map or something, where your optimum need to be located in multiple directions. And that's just 2D, but you can imagine that this could extend to any dimensions. And the algorithm is going to change pretty significantly depending on dimensionality. Then the one that we already talked about is the algorithm will change depending on whether you're looking at maxes versus mins. They don't change too much, but they do change. There's also this whole area of having constraints. So you can have a completely unconstrained or constrained optimization. So let me give an example of a constrained optimization. So let's say you had a function that was measuring profit, and the profit is for regular or premium gas. So just think of the first variable as regular and the second variable as premium. And let's say that you want to maximize your profit. Oh, yeah. And so that's the function that you're trying to maximize, but that there's constraints with those materials, like you have some equation that constrains the amount of material that's available. Maybe that's the amount that can be held in that system or something. So this would be an example of a constraint. And any numerical methods textbook typically covers optimization, and actually I think that for constrained optimization, the best software tool is Excel, actually, for unconstrained or constrained optimization, because there's just a lot of conditions that you need to connect with each other. You can do it in MATLAB as well, but a lot of these kinds of optimization problems are done in industry, and Excel has developed a lot of tools to be able to do them. And then the last one is the linear versus nonlinear optimization, which also would change the type of algorithm. So what we're going to be writing in this class for topic 12 is we're writing a one-dimensional, unconstrained optimization code. I don't think I brought the thing. And I'm pretty sure we're finding, oh, the minimum. So what I'm going to do today is I'm going to write the algorithm for the maximum, and the only thing that you'll need to convert for your lab is writing it for the minimum. And there's a lot of different methods for this, so what we're going to be doing is something called the golden search algorithm. You'll see this as a root finding algorithm as well. And so I'm just going to go through the steps of the algorithm and explain a little bit about the golden ratio that's used for this algorithm, and then you should be able to convert this pseudocode into MATLAB code. So the idea is that you can take any function or any data, x versus f, and you are going to have the algorithm locate the maximum, and this is something called a bracketing method, meaning that the whole method is based off of finding the two points that bracket the maximum and continuing to iterate until those 2 points get closer and closer. So to start this algorithm, you have to have a set of data or a function that depends on one variable. And then to start off the algorithm, you need those two bracketing points. And so bracketing methods don't work unless you can at least pick 2 points that bracket it. So a lot of times you can start with just like the two ends of the function domain, where the XL is the lower bracketing point and XU is the upper. And this method uses something called the golden ratio. And the golden ratio is this number, the square root of 5 minus 1 over 2. It's approximately 2/3, but not exactly. And this is what the Fibonacci sequence approach is. And it's this ratio that a lot of things in nature are based off of. And it has this like symmetry that if you have like this rectangle, and you make this side 1 and this side the golden ratio 0.6, and then you divide the rectangle again and make another division, and this is 0.6, then it like continues forever. And I'm actually going to show you this video because it's a lot better than my explanation. This is Donald Duck and Mathmagic Land. Have you guys ever heard of it? Mathmagic Land. It was, I think it's in the 60s. It's really old, like way older than me. Like this makes me look so old, but this is just something I used to watch all the time when I was little. And I don't know why we had this video because it's so old. But it talks about this ratio and shows you why it's so significant. And it actually is used in the algorithm. Like it has a purpose. It's not just like a fun thing. So we'll have Donald Duck explain it.
It was our old friend Pythagoras who discovered that the pentagram was full of mathmagic. The two shorter lines combined exactly equal the third, and this line shows the magic proportions of the famous golden section. The second and third lines exactly equal the fourth. Once again we have the golden section. But this is only the beginning. Hidden within the pentagram is a secret for creating a golden rectangle, which the Greeks admired for its beautiful proportions and magic qualities. The star contains the golden rectangle many times over.
Sorry about that.
It's a most remarkable shape. It can mathematically reproduce itself indefinitely. All these rectangles have exactly the same proportions. This figure also contains a magic spiral that repeats the proportions of the golden section into infinity. To the Greeks, the golden rectangle represented a mathematical law of beauty. We find it in their classical architecture. The Parthenon, perhaps one of the most famous of early Greek buildings, contains many golden rectangles. These same golden proportions are also found in their sculpture.
This kind of goes on for a long time, but it's like kind of mesmerizing. But it like goes on to show other places where it happens in nature, and it's really the ratio that's important. I'm wondering if this is called the golden section. I think I might be missing that word. But anyway, so this ratio is used basically to divide up the region that you're bracketing, because it allows you to eliminate the calculation of a function the next time. So if we continue on with the steps, I'll explain that a little bit more. Is this too dark? Yes. Why?
I just see the start recording button there.
Oh, this here? No, it's recording. Okay. Yeah. This is to record using this software. I'm using QuickTime to record. So the third step, after you have bracketed 2 points that bracket, you need to choose 2 interior points based off of the golden ratio. So the first thing that's done is you need to calculate the distance that you're going to use based off of that like 2/3 ratio basically. So you're going to take that R percentage and you're just going to multiply it by the size of your bracket. So this looks like this. You have X and F. There's a mistake there. So D is going to be the distance away that you're going to calculate these other 2 points. So X1 is going to be that distance, that think like 2/3 or 60% distance away from the lower point. So X1 would be like right here, and this is D. And then your other point, X2, will be calculated from the upper point, the upper bracketing point, and subtracting off D in the other direction. So it would be maybe around here, and that's D from XU. And you know, you could choose any distance there. You could use half, you could use 0.6, you could choose any percentage to move in from either side. I guess you couldn't use half, anything more than half you could use. But once you get those 2 interior points, you're going to evaluate the function at those 2 points. So the way we're writing this algorithm, it does require that we have a way to evaluate the function at points other than the original data. This can either be done with interpolation, which we're not going to be doing, or with the lab that we're working on for this, there's a analytic function that they're finding the optimum for. It's I think it's optimizing drag. Yeah, because it's minimizing. So once you evaluate the functions at these points, then you are going to compare them with each other. So if the function value at x1 is greater than the function value, if the function value at f2 is greater than the function value at f1, then you know that you can remove the section from I'm writing a maximum, right? I said I was writing a maximum. Okay, so if f2 is greater than f1, did I write this wrong? Let's write it out. So if f2 is greater than f1, then we have our lower point, our upper point, x2, and x1. So let me actually write this. Oh, I wrote it wrong. That's why. That's why I wrote it wrong. F2 is actually less than. Okay. Your lower point, your upper point, your x2, and your x1. So in this case, you have your f1 greater than your f2, right? So you can see from just from the image of those function values, if f2 is less than f1, then you can take this region right here and you can remove it, right? If you know that f1 is greater than f2. And that's the same thing when you're writing the code as just replacing the lower bound with x2. And now your new x lower bound is going to just be this x2 value. On the other hand, if f2 is greater than f1, so in this case you're going to have your upper and lower bounds, your x2 and your x1, but this time the function max is located on the other side. So here you're going to remove this part of the domain. So that's removing from x1 to x upper, or it's the same as setting your x upper equal to x1. And since you guys are writing minimum functions algorithm in your lab, what would change with the minimum? Any ideas? That's an open question. So here we're checking if f2 is greater than f1, right? And we're removing the section on that side. What time do you have class?
10:50.
Oh, 10:50? Okay, we'll finish up. Thanks. So it would be the same, but you're just going to reverse the inequality. f1 is less than f2 for this one, and f2 is less than f1 for this one. So that's what you guys are going to do in your lab. And then the last step of this algorithm is to repeat steps 3 and steps 4 until some condition is met. So basically you're going to keep repeating this process until the UL and U upper, the U lower and U upper, are really close together. And you can set this EPS value, this epsilon value, to some small number. You don't want to set it to 0, just like we've done with other error algorithms. And you just want to keep repeating that, finding that bracket, checking the function values until they're small enough.